Hey guys, so this is the start of our new unit about heat energy. So it's not going to be a very long unit because we don't really have that much time left in school. So it's going to be pretty brief. So just to get started, make sure there's that note document up on Moodle that you guys need to make a copy of, or it'll force you to make a copy. Have that up, or just have like your own notebook with paper to write down notes. And when you're watching this video, you're going to need to write things down, so make sure you're going at your pace. And if you need to, you can always pause, go back, write something down. That's the beauty of the videos. So at this point, you should have watched the video that introduced you to temperature versus heat and what those mean. So a lot of the times it can be confusing, and a lot of people think that heat and temperature are actually interchangeable and that they are the same thing. But if you remember from the video, when it talked about heat, heat was the quantity of hotness, right? So the amount, whereas temperature is the degree of hotness, right? So in the video, the degree of hotness, right, the cup was 100 degrees Celsius, the bucket was 50 degrees Celsius, and the quantity, right, the bucket had more molecules, more particles, so it had greater heat, but was sitting at a lower temperature. So heat is also a form of energy. You'll hear that probably often, or if you go online and see anything, a lot of the times when you talk about heat, you say heat energy. So for heat, the unit of measurement, which you guys may have heard of this before since it is a form of energy, is joules. So we use a capital J when writing that unit. And for temperature, of course, we've got degrees Celsius, which is what we're going to be using in regards to heat and temperature. But you guys have also seen before Kelvin with all the gas law stuff. But again, our focus when it comes to heat is going to be degrees Celsius. So in regards to heat, one of its properties is that it flows from hot to cold. So for example, if you have something hot and you place it on the counter, that heat is actually going to flow into the counter. So for example, right, a hot cup of tea, you leave it out, that heat is going to flow out of that system to the counter, to the surroundings. So it always goes hot to cold. And with temperature, this is going to increase when it's heated, and then will decrease when it is cooled. Okay, so now we're going to get into our thought experiment when it comes to heat and temperature and quantity and how all of these things work together, because we did see in the video that mass plays a part, temperature plays a part. So now we're going to experiment and figure out what roles they play. So one thing that's really important I want to point out, and this is also on the note document itself, if a dependent variable, so our dependent variable is going to be heat, depends on two independent variables that are changing, then the dependent variable depends on the multiplication of those two independent variables. So that's what we're going to be seeing actually when we do our experiment here. So in our first setup, we see that we have a temperature of 10 degrees Celsius and it's going to increase to 20, and we have a quantity, we have a mass of 50 grams. So in order to raise that temperature, we're going to need a certain amount of energy, which we know as heat. So we need a certain amount of this, and we use a lowercase q to represent this when you write it out. So our change in temperature is 10 degrees Celsius. Okay, so again, we need this amount of heat to raise that mass of 50 grams 10 degrees Celsius. So now if we move on to our second setup, so notice that the temperature here, 10 degrees to 20 degrees, so that temperature change is still just 10 degrees Celsius. And by the way, you calculate your change in temperature by taking your final minus your initial, just so everyone knows. So in our second setup, if you guys notice, the mass has now increased to 100 grams. So our mass, when we compare to the first one, has actually doubled. So when we're looking back at our first setup, we said that it required this amount of heat in order to change the temperature of that quantity 10 degrees. So if I double my mass in my second experiment, that means I'm also going to have to double the amount of heat that I need to raise that quantity 10 degrees Celsius. So that's an important thing to understand, because now we see that Q, so heat and mass, are actually proportional. So that's going to be something useful at the end when we're kind of putting all of these relationships together. So now if we go down and we look at our setup 3, we're going to compare to our first setup as well. So notice now that our temperature goes from 10 to 40 degrees. So your change in temperature is 30 degrees Celsius, unlike setup 1 that had 10. So we also see that our mass is the same as our first setup. So the only thing that was changing is that the change in temperature tripled. So based on that idea, that's telling me that the amount of heat that I'm going to need to get my 50-gram sample to increase by 30 degrees, I'm going to need to triple the amount of heat that I use. So not only did we see that mass and heat are proportional, but now we know that Q and our change in temperature, so heat and the change in temperature, are also proportional to each other. Okay, so now we're going to look at our setup number 4 in comparison to setup 1. So our change in temperature, 10 to 40 degrees Celsius, so it's going to be 30 degrees Celsius. Our mass is 100 grams. So comparing 4 to our setup 1, our change in temperature tripled and our mass was doubled. So this is why at the very beginning I mentioned this. The dependent variable depends on the two independent. So dependent would be our heat, and our independent variables are mass and change in temperature. So it tells us that the dependent variable depends on the multiplication of the two. So we take 3 times 2, and that would mean that I need 6 times the amount of heat that I used in my setup 1 to achieve this change in temperature with this amount of mass in my setup for number 4. So now, keeping all that in mind, we can take a step back and say, well, what does this experiment actually show us? So we determined that heat and mass are proportional. Okay, heat and change in temperature are proportional. So using that and using this right here, we can take that and create an equation. So we can say that Q is equal to mass times change in temperature. So if we need to calculate the heat of a system, this is something we're going to use. But there's a catch to this. So in our experiment, we had a certain substance, but not all substances are the same. So substances absorb and release energy at different rates. So when I say this, I want you to think about how long it feels like it takes to boil water. And that's because water specifically is something that it just takes a lot of energy to get it to heat up. So these different substances will absorb heat at a different rate from each other. So you have to take that into account somehow with our equation. So in order to do that, we use something called the specific heat capacity of a specific substance. And so we use a lowercase c to represent that. So this is a constant value, something that you can look up or will be provided to you. So you have to include that in your equation. So when we do that, this is what we get. Q is equal to mass times specific heat times the change in temperature. So remember, Q is heat measured in joules. Okay, M is mass, and it's going to be measured in grams. Then change in temperature, and that's going to be in degrees Celsius. And then little c, the specific heat capacity. Again, this will be provided to you, and its unit is joules per grams degrees Celsius. So you could also write it like this. Okay, either one. So this equation is a must know when you're setting up calculations trying to find heat. So one thing to talk about, what does it mean if you have positive Q, negative Q? So positive heat versus negative heat. What does that even mean? So if you think about just for a second, if you have an increase, so a positive, that is going to mean that you are gaining heat. The word we use is absorbing. So we're going to be absorbing heat. So if it's negative, that's going to be a loss. So you are losing heat. Typically use the word releasing of heat. So this heat that's being lost could be going to the surroundings, it could be going to a different system. It is just no longer part of whatever you are testing. And then when you're gaining heat, this could be something that you're specifically doing. So we've done this a lot where during an experiment, we need to heat something up. So we introduce heat into that system by using a hot plate. So that's just an example of what that would mean and what that would look like. So just real quick, I want to go back to our equation, and I do want to clarify, at this point for us, we don't have enough time to go into utilizing and doing calculations for heat. So this is a just know, recognize, understand how we came up with this, but you are not going to actually have to use it in our class this year since we're kind of out of time. But you can take this concept and use it conceptually. So that's what this question is asking you to do. Which substance would be better? So think more efficient at storing heat. So now you just compare substance 1, substance 2. So substance 1, we've got 10 grams, and it is storing 10,000 joules of heat. Okay, so substance 2 is 5 grams, and it is storing the same amount of heat, so 10,000 grams. So which one is better at storing this amount of heat? Which one is more efficient? So because substance 2 actually has less mass and it's holding on to the same amount of heat as our substance 1, that tells us that substance 2 is actually better at storing the heat because it takes a smaller amount to do the same job as substance 1.